Good morning, guys. So today we just have a couple of topics left to complete your module one. Okay, and so far what we have seen, at least in the last few classes, we saw the different performance metrics and also different factors that affects your parallel processing, right? We also saw about different supercomputers, the grand challenging problems, and the list of top supercomputers, right, and so on. Today we will revisit this speed up. Okay, so far we've actually seen speed up in more than one occasion now. Uh, so speed up in general means it's the ratio between uh, the old execution time by new execution time. That's what it is, very simply said. The old execution time is the execution time that for a program to program that takes to run on a uniprocessor or a non-enhanced processor. Okay, and after some enhancement, like you bring in some parallelism into it, you enhance this system, and then when you again run the same program, you expect it to complete faster. Okay, so that the old execution time will be longer, right? It will be bigger than the new execution time. So when you take the ratio, it tells you how much faster your new system is. So, to give a small example, we saw a naive example, right? So we have one old computer, and then in that computer we ran some program. It took 100 seconds, and then we enhanced the same laptop or computer, and then when we run it on this new system, same program, it is running at 10 seconds. Okay, so now what was the speed up? And we got somebody who said it is 10x, correct? So how did we get the 10x? It's simply by dividing 100 divided by 10, old execution time by new execution time. Okay, so now we will revisit this speed up performance loss. We are going to go explore this or delve deeper into this speed up. And why we are dealing with speed up is because this is one of the factors which we use every day to measure performance. Even though I keep stressing that there is no one metric to say this is good or this is bad about processors. So we can't directly have like one metric to say this metric will say this processor is good. There's no generic law like that. It really depends on the requirement. But speed up in general has been one of the factors that's widely accepted. It's not the rule, but it's widely accepted. If generally speed up is good, then it means it's a good processor to have, right? So, uh, so that's why we are actually exploring much deeper into this. So we will revisit Amdahl's law. Okay. So Amdahl's law for a fixed workload. So far, what we have seen is a fixed workload model. Like I was saying in the last session. So fixed workload means that you are not going to change the program. Okay. So you have a huge matrix multiplication problem. Let us say you're dealing with, like, say, 1,000 by 1,000 matrix multiplication you want to do. Then what you do is you will run that 1,000 by 1,000 matrix multiplication on your old system. Okay, and then you enhance the system and you run the same matrix multiplication, same 1,000 by 1,000 matrix multiplication. Maybe you will parallelize it or do something about it, but the size of the matrix multiplication is still going to be 1,000 by 1,000. Okay, the problem size is not going to vary. Okay, so that's your fixed load speed up. So Amdahl's law states that only, right? So Amdahl's law states that you have the same workload, you're not going to change the workload, but with the same workload, you're running it on a non-enhanced system and an enhanced system. What is the speed up you get? Okay, so now if you consider a degree of parallelism I, and let us assume that this I is greater than n. Okay, and n is nothing but your machine size. Okay, the number of processor. then you will say the execution time of wi. Wi is nothing but the workload. Okay, the workload uh, at the time instant I. Okay, not the time instant I, workload at the instant I where your degree of parallelism is I. Okay, so you can actually categorize your entire workload into several workload slots, like something like this, right? So if you have a workload W, then you can actually split this into several parts. Okay, and then you can say that specifically you can actually split this to m parts. Okay, where each of these part is going to say my degree of parallelism is one or the other here. Okay, so here I'll have one degree of parallelism, here I will have one degree of parallelism, here I'll have one degree of parallelism, and so on. Okay, so this is exactly my workload. Okay, how many instances of time my degree of parallelism hits this, so I will have some number here. So it's basically it's going to look like a bar chart, right? And so this is nothing but your parallelism profile. That was the first topic we saw in this chapter, correct? A parallelism profile is nothing but the degree of parallelism over time. Okay, so you're going to have a workload profile like this. So now what are we going to do? So we are going to come up with this equation for execution time for the instant where the degree of parallelism is I. So that will be given by your workload divided by I times delta, where delta is nothing but the computational capacity, right? The MIPS or flops. So that's the computational capacity of your uh, machine. And then you have this function, okay, a ceil function of I by n, and you merely have this I by n only because you have now assumed I greater than n. Otherwise this formula is same as the one we saw in one of the earlier classes. Okay, so ti of n, we simply had wi by I delta, that's all we had. But here, since we are assuming degree of parallelism I could be greater than n, meaning your workload could be bigger than your machine itself. Okay, so then in that case you may have to add this factor I divided by n. Okay, so there is a ratio here and you take the ceiling out of this. Okay, why ceiling is because you're going to assume the worst case time. Okay, so you just round it off to the next integer. Okay, so that's how you get. And response time is nothing but the overall execution time. You get that by summing these individual time slots. Okay, so thus you have a summation of I equals to 1 to m wi by I delta and I by n. And then speed up, we know the speed up formula. Speed up formula is actually t1 by tn. Okay, so that's all it is. So t1 by tn, and so when you substitute that, you get this summation of wi by wi by I into this I by n, correct? So so why we have wi here is because so this is the workload at t1. Okay, so wi at t1 you have it as sorry t of 1 you have it as wi from 1 to m. Okay, so it's going to be same as that of your parallel algorithm as well. Now you're going to add one more factor here called q of n. This is just to make it a generic equation. So here in this, right, in this equation, like previously we had the speed up equation t1 by tn. There we did not consider any overhead. We only considered the sequential part and parallel part, correct? But there could also be communication or IO overhead. So you include that overhead also into this. That overhead is represented by your q of n. Okay, so that's all this is. And now when you want to revisit Amdahl's law, what you have is your Sn. So you're just going to expand this formula. Okay, and then you're going to for now ignore your q of n. Uh, and if you expand this formula, Amdahl's law, you just assume two things, right? So first thing is you have a workload that has completely sequential part and then a completely parallel part. Okay, so here your DOP will be 1, and here your DOP is going to be n. Okay, so that's what Amdahl's law is about, correct? So you just have two scenarios. There's nothing in between, you'll assume, for Amdahl's law. Okay, either it's a simplistic law, right? So either you have a sequential part, so alpha percentage of time you have sequential part, and then 1 minus alpha percentage of time you will have a completely parallel part. Okay, so that's why you have only two cases here, w1 and wn. Okay, so now if you substitute that in this formula, you get the new speed up formula, which reflects Amdahl's law. It's w1 plus wn by w1 plus wn by n itself. Okay, so you just have to rearrange this equation. Any questions on this, guys? Hey, are you guys following whatever I'm saying? It seems like not. Understanding? Are you sure? Kind of. Okay, that's not a good answer. Seriously, man, that's the worst compliment you can give me. you know, of course, yeah. If I study, I'll understand better. Yeah, man. Yeah, yeah. But there are not too many problems here. But yeah, yeah, it's fine. But anyway, I hope at least you get the big picture, right? I mean, of course, you have to actually go through the book. But I hope you guys understanding the concept here. Okay. So no, okay. Thanks anyway. Okay, so now let's look at this graph. Okay, so this is what the fixed workload means, right? So you just for Amdahl's law, you just assume two scenarios. Okay, one is the sequential part, the other one is the parallel part. Okay, so now in the sequential part is represented by W1 and parallel part is Wn. And even if you increase the number of processors, okay, even if you are expanding, enhancing the system, you just have the same workload. Your workload, the number of computations that you are going to do in your workload is still going to be the same. You're not going to increase or decrease that. Now if you have that, then what will happen to speed up? Okay, speed up is going to improve, right? In other words, your execution time is going to come down. Okay, as you see here, your sequential part is staying the same. Okay, you just have that square t1 block that is fixed, that's not enhancing at all. Okay, if you see the area of this t1 is the same. Okay, everywhere your t1 is not changing, t1 is fixed. Okay, the only thing that is changing is your tn, and because tn is reducing, the overall time is also reducing. Okay, you get the curve like this. Okay, and you have to keep in mind that this t1, right, is will not change, and that is going to impact your speed up. You will not get as much speed up as you are supposed to get, because there is some portion of your code that will not change at all. Okay, so that's what you have to take away from this graph. Okay, so the idea is, as your number of processors increase for the same workload, you can expect the speed up to be better, or your execution time can will reduce. Okay, so the other way of looking at this graph, right, is like this. So when you have a sequential program, and this is your alpha. Alpha is nothing but how much sequential fraction you have in your program. Okay, initially you assume zero alpha, which means my program is completely parallelizable. Okay, so then you have 1024. If you, I mean, like, it's just a number they've picked, so you get n times speed up. N is the number of processors, n times speed up you will get. Okay, and now on the other hand, other extreme, if you have 100% alpha, it means there is no speed up for you. Okay, because your program is completely 100% sequential, so it doesn't matter how many processors. Even if you have 1024 processors, your speed up will still be the same. You will just have 1x speed up. Okay, and then you have this curve like this. Okay, so this is how this Amdahl's law curve is going to look like. Clear? Okay, so now going further, so there is this person Gustavsson. So he actually explored this a bit, and he wanted to explore into area where it was found that see, when I want to increase my uh, computational power, I will not, I may not be running the same algorithm, right? See, for example, you say, uh, let us say you have an old mobile phone, right? We'll just pick one naive example, an old mobile phone with old camera and all, right? Then the YouTube video that you play when you had that old phone like long time back will not have that much frames per second or anything, or maybe the games that you play, right, may not have that much frames per second. We used to have this snakes game, I remember, in the first Nokia phones. So that was the computing power we had at that time, and the game that we used to play was the snakes game, correct? So now when your computing power increased, now you're not running the same snakes game, correct? Now your game algorithm is also changing, so your demand for your computing has also increased. So you have to play videos that are much faster, much enhanced with higher dpis, and then you play the games that, then more realistic first person shooter games that are there in present mobile phones. So your application demand also increases, okay? And now Gustafson, he focused on this aspect. He said, okay, see, the workload may actually grow as well. Okay, so in other words, if you have a 1000 by 1000 matrix running on say a 10 processor system, now I buy 1000 more processors, then I will not be running the same 1000 by 1000 matrix, correct? I'll be running 10,000 by 10,000 matrix. That will be my new requirement, correct? So in that case, what happens? Okay, so now my here the focus is on higher accuracy. Okay, so why am I doing all this? I need more accuracy, like more frames per second, or I need accuracy up to like 10th decimal or 100th decimal or something like that, especially true for scientific applications like weather prediction and ocean modeling, right? So when you think of all that, then these higher accuracy and precision matters. Now then what happens is, I may not be focused on increasing my speed up. Okay, what I'll be focusing on is I'll have a fixed time speed up. Okay, I'll fix the time, execution time, I want it to be the same. See, my 1000 by 1000 matrix multiplication took 100 seconds. Now on my new system, I'm okay with 100 seconds. Okay, I'm okay with 100. You take 100 seconds, but give me 100th decimal accuracy. Okay, 100 decimal precision, if you give, I am okay. So that is how you bargain here. Okay, so now if you assume that w dash, okay, w dash is your new workload computation. So obviously your computation is going to go up, correct? So you would represent it by w dash. Okay, so w1 dash is same as your w1. Okay, so which means that uh, when you have a uniprocessor system, it really does not matter, right? So w1 dash and w dash are going to be, w1 and w1 dash are going to be the same. And similarly the time it takes is also going to be same. T1 and t dash of n of 1 is going to be the same. Okay, so now if you now if you actually compute the total workload, so we need to know what is the total computing capacity of this problem. Then it is represented by I equals to 1 to m of wi, correct? Now if you expand this, this is nothing but your wi dash. Okay, it's wi dash by I. Okay, and with a seal of I by n. Okay, so now what you're saying here is that the time it takes for your workload wi and the new workload, the enhanced workload wi dash, you need both of these to run at the same time. Okay, so it means this computing power, this computing algorithm and this computing algorithm are going to say take the same time. So you equate this, you get this equation. Okay, so you're just saying this time and that time are equal, and this is the enhanced algorithm. Okay, enhanced workload. Now if you compute speed up, you speed up your w and w dash are same for t of 1, correct? So you substitute your t of 1 by t dash of 1 and you get this wi dash. Okay, and then you have the enhanced algorithm. Enhanced algorithm computing is given by this expression. Okay, or in other words, you speed up here, you represent it as your summation of wi dash by summation of wi. Okay, so this is your speed up for fixed time. Okay, so fixed time speed up. And here the advantage is you have fixed time, but then your accuracy will vary. And then if you represent it again in terms of Amdahl's law, kind of an assumption, right, where you have only two extremes, like one sequential, completely sequential, 100% sequential, and one part it is 100% parallelizable. So then you get this new expression as given here. Okay, and the corresponding graph is going to look like this. Previously, if you remember, we had a constant workload, correct, for Amdahl's law. So you had a constant workload, but now when you increase the number of processor, you're also going to increase the workload. Okay, the workload is also going to increase. Okay, however, if you take the execution time, it's going you're going to maintain the same execution time. I will make sure that I don't want any benefit in time. Okay, I just keep the same execution time, but I will increase my accuracy by increasing the problem size. Okay, so now when you calculate the speed up, it's almost flat, but then there is going to be like a small dip. It's actually very good curve here. Okay, if you compare it to your Amdahl's law, how did it actually exponentially decayed, right? It flattens out as you reach alpha equals to 100%. Okay, but here it is not the case. Okay, why? Because you are maintaining the same execution time. Okay, and then it's just going to be linearly it's going to decrease. Okay, so that is how this speed up is. Okay, any questions on this? Okay, thanks. Okay, so now we go to the third part where you see that there's not going to be this also, right? So you may not have your time also fixed. Maybe I need shorter time, we will not know, right? So if you think about it, however, my I'm always limited by this area, and then because of that I'm always limited by my memory. Okay, so the actual limit is my memory, how much computing I can do. Okay, given given a memory model. Okay, so given a memory capacity, how much computing I can do. So this leads us to this fixed memory speed up. Okay, so here we are going to represent our workload in terms of a function of memory. W is g of m, or you can also represent m is nothing but g inverse of w. Okay, so now you're also going to say that w star of n is represented by g star of nm. So this is the workload running on a parallel machine with n processors. Okay, now this one you're going to represent it in terms of this function g, capital G of n times small g of m. Okay, so this is how you're going to represent this, only for your representation purpose, where your g of n is a function, how it says how much increase you get in your workload as your memory increases n times. Okay, so let us say your memory this just compares when your workload increases, how much your memory increases. Okay, so that's the relation that we are going to draw out here. Okay, it's a function of increase in workload as memory increases n times. How much you can enhance your workload if you have your memory increasing. Now again substituting the same way, you get this, so wi star instead of your other wi dash. Okay, and other representation is going to look like this. There is one additional factor, you are going to have g of n, a factor that is being added here. okay, where you're bringing in your g of n as the growth of your memory increase, okay, as your workload increases. So now this becomes the generic speed up law, okay. So it's going to look something like this, okay. So my workload is going to increase, and also my time might also increase because I'm also having my memory that is going to increase. It can also decrease. It depends on how you're going to have this. It's not a constant execution time. Okay, you may also have a decreased execution time. That really depends on how much your workload is increasing. Okay, so this gives us more flexibility in terms of a formula, right? So it gives us more flexibility of putting everything in one equation. Okay, so if you substitute g of n equals to 1, this will become your Amdahl's law. Okay, your g of 1 becomes 1, it becomes your Amdahl's law because my workload is not going to increase at all. Okay, the second case, g of n equals to n, so it's going to linearly increase with my increase in the processor size, right? That's your Gustavsons law. That's what he says. The workload increases linearly with my increase in the computing power. That's your Gustavsons law. And all the other cases, you have this fixed memory model. Okay, so where it's going to cover rest of the cases. So this one formula covers all the cases of your workload growth with respect to your increase in the computing power, computing demand, as well as the memory size. Okay, any questions on this? Okay, if not, then we'll move on to the next topic. So this is it's a short topic only. It's scalability analysis and approaches. Okay, so we are going to revisit scalability. Scalability is very important because there's no point in just uh, uh, adding more processors that doesn't give you any benefit. Okay, so always have to be this return on investment, correct? So so the scalability depends on so many factors as mentioned here. Okay, so we have these scalability metrics that really depend on your machine size. Okay, so that's n that we were seeing, and then it depends on your clock rate. So clock rate f, so how much so in other words, the way to read this is when your machine size increases, right? So if I enhance my processor from 100 processor cluster to 1,000 processor cluster, am I going to get 10x speed up, or what is the speed up I'm going to get? And similarly, next is clock rate. Now if I actually increase my clock rate from 2 gigahertz to 3 gigahertz, what is the benefit I'm getting? How much speed up I'm getting? Okay, and similarly the problem size, if I increase my problem size, how much I get? And then my CPU time. Okay, so this is the total CPU time that I have, and then IO demand. So IO demand also matters, right? So how much so when your IO demand increases, it's severely going to affect your scalability. And this is what we saw about the overhead. This was reflected in our equations as the IO and communication overhead. And then of course the memory capacity, so we saw in fixed memory model. And of course there's going to be communication overhead. So this is different from IO demand, right? So IO demand is strictly deals with the IO uh, uh, devices. Okay, but communication overhead is the overhead when you have any two blocks communicating. Anywhere you have a protocol, right? It doesn't have to be IO device, but anywhere you have some kind of protocol, there's going to be overhead. Okay, because there's always going to be some handshake that goes on between any communication, so that you will have some communication overhead. And then you have your computer cost. Okay, so the cost, it may not be as simple as you think. Okay, if I actually buy a 1,000 node a cluster, it's going to cost 1 lakh, let us say, a very I mean, like yeah, uh, best case scenario. let's take 1 lakh. Then if I actually buy a 2000 node cluster, it may not cost 2 lakhs. Okay, it could be either way. It could actually be 3 lakhs or 5 lakhs, or it could actually be lesser than that also. We don't know. It may not linearly, or it may not be a very direct function, because it really depends on what kind of topology, network topology you are using, and then what are the different stacks that you are using to connect, and all these things, right? So there's always this fixed cost, variable cost, and all these things. And finally, your programming overhead. Okay, so everything finally you'll also be limited by your software parallelism. So you also have your programming overhead, where you will not be able to do any better than this. Okay, so if for example, if you have to get 1000 inputs from your user, then you have to get 1000 inputs sequentially from the user. You have to enter these 1000 inputs by hand, right? So something like that. So it's always there is always this one part of your program that you cannot optimize. Okay, so that's the sequential part that we were seeing, right? So these are the different overheads that will affect your scalability. And once more, we will revisit the speed up and efficiency. So speed up again, given by s of s comma n, where s is your problem size and n is your machine size. Then you get the speed up as nothing but t of s comma 1 divided by t of s comma n plus h of s comma n. H is the overhead. This is t1 by tn. It's the same formula here, but here you're assuming s. And here, may I ask what assumption is it making? So, which uh, model this resembles? Can somebody say? Hello. So this is going to reflect the fixed load model, okay? Because my problem size is not increasing. Okay, so this is my fixed load model. You guys can hear me, right? And then you have efficiency. Efficiency is nothing but the speed up divided by the theoretical maximum speed up. Theoretical maximum speed up is of course n. So this is what your efficiency is. Okay. The system is scalable if efficiency equals to 1 for all algorithms for any n and any s. Okay. So a system is scalable when you have efficiency as 1. Then scalability definition. So we'll have scalability. Scalability properly defined is your phi of s comma n. It's a ratio of your asymptotic speed up s of s comma n, and then your asymptotic speed up s ideal. Okay, so it's just the ideal scenario of your asymptotic speed up. So it's given by this. So t of s comma 1 by t of ti of s comma n. Okay, so now if you substitute, then you get your 5 as 5 as ti by t of s comma n. Okay, so that's all about your scalability. So where do we use this? We'll just quickly go over this. So you have your t, your time, and then your scalability. Sorry, your speed up, and then your scalability. So if you have all these things, right? So when you actually, you can actually draw out. So for a given machine architecture, you can actually find out the complexity of all these. And then as you see, the scalability of your hypercube and omega network are actually very good. Okay, so so you can actually infer that. So you can always say which network is best, right? So you have a better scalability in hypercube and also in omega network. So evolution of all scalable computers. So far this is only a trend. So Cray used to be really popular, and then later NEC. Okay, so this is how it has been. Intel and all these things are all already there. And this graph has now changed quite a bit. So, but let's not go into the more recent one. So just you have it in your textbook. So just for your information. So evolutional path, size, scalability, generation, time, problem scalability. See, these are some of the things that we need to consider or go over, right? So where are we going, and how are the problems scaling, and so how are the generations, like how it evolves over time, and how my problems are evolving, what kind of new problems am I working on. So these are some of the things that we want to go through. Okay, so now I'll not explain this in too much detail. You can read when you get some time. So these are some of the research problems that are there, and what are the solutions available. So we'll just pick one here. So when you have, let's say this, right, multicache inconsistency. Okay, so when you have, we actually have this quite often. When you have multiple processors and each processor have their own cache, there is a lot of possibility that the cache is inconsistent, meaning the let us say a variable I. So I have cached it in my cache, and somebody else would have cached it in their cache. And how do we deal with this consistency? So there has to be some communication, right? So how do you do that? So you have to come up with new cache coherence protocols. Okay, so this is the proposed solutions for these research problems. Finally, we have supporting issues. So you need to focus on software scalability, and then reducing communication overhead, enhance programmability, and provide longevity and generality. Okay. So with that, we come to the end of your chapter 3 and your module 1. Okay, it's fairly exhaustive, and so please go through your textbook. This is your textbook, and most of your figures I've taken it from your textbook, or from Wikipedia, or some random site that Google Image had pointed out. So if you don't have any questions, I think we are done. All right. Well, before you log off, right? So just hold on a bit. Okay. I just stop recording.